this session, we're going to look at Boolean algebra simplification and formulation. Just to go back to what we did last time, we've looked at the individual logic gates and or XOR, NOT, and so on, and we've seen how to combine them into a logical circuit and be able to compute with this combinatorial logic circuit the output Q in terms of inputs. So we're going to take up this particular example in our tutorial class, so do make sure you work on it. So in today's session, we're going to look at Boolean algebra simplification and problem formulation. So here we're going to look mostly at mathematical formulations and one fundamental law which is very useful in simplifying logical expressions, De Morgan's law. So we're going to cover that. Now, when you're covering the logic gates, if I just scroll up, when you're covering the logic gates, you'll remember for each logic gate, for example, for this one, for the XOR function, you'll be able to write a mathematical expression called Boolean algebra. Similarly, if we consider the NOT operation, it was written like this with mathematical expression, and the N logical function was a dot or a cross, and the O was a plus sign. Okay, but remember these operators are not the same as we use them with decimal numbers. They are symbols which operate on Boolean variables. Okay, so you can see here very similar to what we've seen above. Here you are doing an operation and then complement. So what De Morgan's laws tell us, we have a pair of them, so two laws. The first law tells us if we take the O-ring of two logical variables A and B and then we complement, it's the same as if you would complement them first and then you would take the end of them. So the counterpart of this is if you take the complement of ending of two expressions, then you can obtain the same result if you take the complement first and now you would OR them. Okay, so this is a very simple form here. Of course, when we apply it to big expression, we'll see how it works out. Okay, now if you want to prove the De Morgan's law, there are many ways you could do that. One way is to construct a truth table. So let's try to do that. Let's try to construct a truth table to show that De Morgan's law holds. So I'm going to use the first one here, and then you can attempt the second one. Okay, so we can see clearly we have two inputs, A and B. So we're going to construct a truth table with two inputs. We've seen earlier that leads to 4 possible combinations. Okay, so let's try to do that. Let's construct a truth table here. With 4 possible combinations. So we have one combination which is going to give us your A, your B, and the next one we want to calculate here is A or B. So we're going to calculate here A or B, and then the complement of A or B. Next one we're going to calculate is not A, and then not B, and finally we're going to calculate A, not A, and not B. Okay. So here we're going to have your input A and then your B. Okay, so next we're going to calculate your A or B. And in this one here, we're going to calculate your A or B complement. Okay, in this one here, we're going to calculate your not A. And this one here, we're going to calculate your not B. And here, finally, we can calculate your not A and not B. Okay, so if we compare this column here and this column and they are the same, it means you have verified that this holds, this expression holds here. Okay, so let's start. We know we have 4 possible combinations. Just draw them. So 4 rows here. And like we said, to make sure we don't miss anything, in the first column here, we alternate every single row. And then here we're going to alternate every 2 rows. And now next we want to take A and B. So we're doing step by step here. We're going to get this expression here. So let's take A plus B first, just like we've done earlier. So operation is just equivalent to adding. So we get a 0 here, we get a 1, a 1, 1. And this in this column here, we want to complement the A or B. So we just negate. So we get a 1 here, a 0, 0, 0. Of course, as you get used to the logical expressions, you can do this step directly. So you can just add it and invert. Now, next, we want to calculate the invert of A. So we just take this column here, invert. So you get your 1, 1, 0, 0. And this one, we want to invert B. So here you're going to get your 1, 0, 1, 0. So finally, we want to take the end of these two columns here. So you just multiply them. So we find that we get 1 times 1 is 1. Then you get a 0, 0, 0. Okay, so if you're comparing these two columns here, so this one and this one, we find they're exactly the same. It means you verify this expression here is correct. So similarly, you can give this similar approach, a truth table approach, to verify this second one. So I'll leave that to you. If you've got any problems, you can come to it during the tutorial session. Okay. Let's move ahead. So these De Morgan's laws are very, very useful. You get to use that in simplifying expressions. Now the question comes, why do you want to actually simplify an expression? You realize if you wanted to implement, let's say, this logical expression here using a logic gates, if you want to implement that in hardware, of course, you're going to use logical gates. If you can simplify an expression so that it becomes simpler in terms of operations or even number of variables you're using, then you're using less of hardware. So it's always interesting to simplify your logical expressions first before you have the hardware implementation. So this is one main reason why you'd be asked to simplify a logical expression. So let's look at some rules now. Some rules, which are some further rules. So we've seen two rules here from De Morgan. These rules here are further rules which are based on the Boolean algebra, Boolean logic, binary variables that you're going to also use to simplify expressions. So let's convince ourselves of these first four here. Okay, so I'm just going to take the annotation tool again and just help you here. So A or A is itself. So convince yourself. How do you do that? So let's say your A is, so A is can take two states because the binary variable, so it can take 0 or 1. So if what you're saying here, if your A was 0, so you can take 0 or 0, you're going to get 0. In case now your A was 1, because A can take two states, then you can take 1 or 1 is 1 itself. So what you find here is whatever state A takes, the output takes the same state. So when A is 0, the output is 0. When A is 1 is 1. So A plus A is itself. Now, second one, A or 1 is 1. We knew that from the old logical operation. If at least one of our inputs is high, the output will be high. So irrespective of state A is taking here, the output will be 1. So imagine A is 0, the output will be 1. If A was 1, it will be 1 itself. It means A is a don't care here. It doesn't matter what state A would take, you would get the same result 1. So in logical expression, if you have anything which is all to 1, the result will be 1. You can just forget about the A here. So again, this is a case here where you can very easily simplify your hardware implementation. In this case, your output will always be high. Third one now, A or A is itself. So let's take a very similar approach to what we did above. So if A is 0, you're going to get 0 and 0, which is 0. You multiply here. If A was 1, you take 1 and 1, you get 1. So again, we see whatever state A takes, output takes the same state. When A is 0, you get a 0. When A is 1, you get a 1. So A and A is itself. So if you apply the same technique now, A and the complement of A will always be 0. If A is 1, its complement will be 0. So the result will be 0. 1 times 0 is 0. In case A is 0 now, then you can take 0 times its complement, which is 1. So again, the result will be 0. So again, in a logical expression, if you have A or AN not any variable ending with complement is always going to lead to the loose state. Okay, let's proceed further now and look at the following. So A and 0 is going to be 0. So anything ended with a 0 is going to be 0. A or 0 is going to be A. So whatever state A takes, if A is 0, you get a 0. If A is 1, it's going to be a 1. So whatever state A is taking is going to be A itself here. On the other hand, here, A and 0, irrespective of whatever state A takes, a result to be 0. Now, A or not A is what? So let's again consider. So if A is a 0, you're ending it with this complement. So you get a 1. And if A is 1, so you get 1 plus its complement, you again get 1. So irrespective of the state A is taking 0 or 1, the output is always 1. So this one is 1. A and 1 is what? So again, if you have any doubt, you can just very quickly test it. So if A is 0, you get 0 times 1, you get 0. If A is 1, it's 1 times 1 is equal to 1. So whatever state A is taking, his output is taking the same state. So this is going to be A here. Okay, so two further rules I want to discuss before we move on and try to look how we apply them in the following expressions down here. So I'm going to do a couple of expressions for you and leave some for you to practice in your tutorial sheet. You would have these expressions to work on anyway. So the next rule which I want you to consider now in light of what you've covered is the following. Let's just change the color to something different. So let's say we have an expression like this: A or A B. Yep. So in this case, you can just factorize the A, and then you have 1 or B. And just factor out A outside, which is common. So we've just seen here anything which is odd with 1 should be 1. This expression we've seen here. So anything which is always 1 is 1 itself. It means this expression here, you can just take out B. This A times 1, so ultimately it's just A. So again, this is a nice example to show to you. If you decide to simplify this expression, you are going to have less of operations. And in this case, you can even eliminate some inputs, which I don't care. If you wanted to implement this part of expression using logic gates, you would have an input A, you would have an input B. So first, if you implement it without simplification, you would first want to do an ending here. So you're first ending your A and B. And the result now is being odd. So you're going to OR the result to get the output. So what you're going to OR, you're going to OR A and the result of ending. That's going to be your output. But what the simplification is saying here is you don't need to do anything as such. Yep, so you can forget about the B, you can forget about all this, because your Q is simply equals to A. That's what the simplification allows you to do. Okay, now let's apply this rule here to another rule which you might come across as your simplifying expression is as follows. So A or not A, B. Yep. So if you have an expression like this where you have an expression A, or you're ORing it with a complement of that expression and ending it with another variable, we can show that this one is simply equal to A or B. It means you don't need to have a complement. Let's see how we do that. So what we've just seen above is if you have A or AB, you get A itself. Yep. So it means you can replace this A here by this expression here, A or AB. See what we've derived on top here. And of course, this is as before, or A like this. Okay. So if you simplify that further now, you can just group the, you can consider these two expressions here. If I'm B common, so it is A, O, and B common, you get A, O, complement of A. So we've just seen if you take A, any variable, OR it with this complement, it's going to give you a 1. So see what we just see here, A, O, complement of A, we obtain a 1 here. Okay, so this one is a 1, it means this one can be replaced here by a 1, and the result will simply be A or B. Okay, so this is what we were highlighting here. So if you have the expression A or a complement of A is B, then you can just take out the complement of B. Okay, so very interesting rules here which we're going to use as well. Okay, so let's move ahead now and try to apply this to one example here. Let's take the first one, and then let's take a couple of them. Let's take the first two here, and then you can practice on the remaining two, which actually will be on your sheet. Let's take this one here and try to simplify this expression. So we are saying A or B first, ending now with O, which is C and D, and all complemented. So if you wanted to simplify this, you could apply De Morgan's rule here. De Morgan's rule told us if you have whole complement here, and remember your ending. So De Morgan's rule tells us that you can now complement first and then all them. So it means if you wanted to simplify this one, you can break it into two parts. There's A or B, so that's the first part. Remember, what I'm applying here is as follows. In De Morgan's, it's A and B whole complement is equal to the whole ring of the individual complements. As you can see here in this expression here, you have an operation being carried out here. So this whole expression here is as if A there, and the C plus D is as if B there. Yeah, so if you have this one now, it means we can take the individual expressions, complement them, and all them. And because here's an end becomes O on the right hand side of De Morgan's rule. So, and then C plus D again, you would have to complement that. Now you can apply De Morgan's rule again now, because now you have A or B whole complement. It means this can be equal to, let me just erase this part here. So it can be confusing here because your A a different meaning in this expression. Just take this one out. Okay, so let's move ahead. So now if you apply De Morgan's rule again, here we have the whole ring and whole complement. So it is the ending now and the individual complements. Or again, this one you complement first and then you end. So you cannot simplify any further now. So you could simplify this expression to this form. This is application of De Morgan's rule. Doesn't mean that you will always apply De Morgan's law. You will have to see when you can apply it. Okay. Let's look at the second one now. The second one is, as you can see, here's the complement, but you can distribute these two brackets just like you would do in mathematics. So let's try to simplify this one. Let's first try to expand the brackets. So you get A, B, A, B. First expression is A, B, A, B. Or just like we do in mathematics when you expand brackets. So the next one is A, B, D. Or A, B, C. Or C, D. Now, as we've seen above, if you have A or A is itself, so you can combine these two. Similarly, B and B will be B itself. So this one simply becomes AB. Okay, when you are ORing it with ABD, so if you can take that common, it's 1 plus AB common there, you can see, so 1 plus D plus C, and all the two is CD. Now anything which is always 1 will be 1, so this whole expression here would actually be 1. The result is simply AB plus all the two is C. So again, you can see how simplified this big expression here into a simple expression needing less of logical expressions, logical variables. And so if you had to implement that in hardware, again, that would be much more simple to do. Okay. Now, the next topic I want to cover in this presentation here, in this pre-recorded video, is universal gates. Okay. So just before we start universal gates, so these two expressions again can apply the rules we covered above and try to solve this due to simplified expressions, and we'll cover that when we do the online session for tutorials. Okay, so universal gates now, what are universal gates? Universal gates are standard gates if you want, because in the industry we tend to go for mass production. So what gates can we use to represent other gates? Universal gates are basically gates which you can use to represent any other gate. Okay, so as it turns out to be, as we'll be seeing down the line, universal gates are the NAND and the NOR gates. The NAND and the NOR gates. Why is it universal gates? Because very simply, we can implement all the other operations we've talked about: the NOT operation, the OR operation, the NAND operation, the XOR operation, or the XNOR operation in terms of the NAND or the NOR gates, one of them. It means if we were to manufacture only one type of gate, because it's very useful if we could manufacture only one gate because of mass production, so we manufacture only one type of gate on the production line, and you can use now this gate to implement other gates, so you don't need to change the settings of the production line. So first, we're going to see how can we use the NAND and the NOR gates to represent the NOT function. NOT function is pretty simple. Just go to NOT A. Okay, so I'm just going to explain that to you, the methodology which you can use, one of the methodologies you can use to represent any gate in terms of the universal gates. Okay, so let's take this expression here. Just go to NOT A. As explained here, we know that A or A is A self. We've seen that above. We've also seen that A and A is A itself. Whatever state A would take, the O-ring would give you A, and whatever state A is taking would end them is going to give the same output A, as we discussed above. It means if you want to complement A, you want to find a complement of A, you can also complement this. If you want to find a complement of A, you can also find the NAND, the AND of the, you can take the AND of A and then complement. So what is this expression here you find? What is this one here? This expression here is nothing but the NOR operation. So if you want to implement the NOT function, the NOT function is, is like this. So A there, and you want to complement it. So what this expression is saying to us, you can also implement the NOT function by simply taking the NOR function. The NOR function looks like this. The NOR function is nothing but the OR and the complement. So if you were to have, because you have only one input, of course, you want to put two inputs. So if you take the input A and then you NOR it together, like this expression is saying, you would get its complement. This is what this expression is saying. Whereas this one here, this expression here is saying to us, if you wanted to implement the NOT operation, you can very well take the NAND of it. Because you are ending and then complementing. This is nothing but the NAND operation. So here you would also get the inversion of A. So as you can see here, maybe this already gives you an idea why the NAND and the NOR gates are actually universal gates. So what we've shown here is you could implement the NOT function. Okay, so if we just scroll down now, or we find the detailed expression, the detailed explanation, what I've just explained to you is again repeated here. So we can read through the notes here and see how we could implement the NOT function in terms of your NAND and your NOR gates. Now, if you could understand that, how do you implement the NOT using the using the NOT, using the NOR and the NAND gates? So it's very straightforward to understand now how we could actually implement the OR gate. That's very simple because the OR gate is simply the inversion of a NOR gate. So if you wanted to implement the OR gate, that's very simple in terms of the NOR gate. But if you want to implement it in terms of a NAND gate, it's a bit more complicated. So let's try to look at these two now. So if you wanted to implement the OR gate, let's draw the OR gate. So we want to implement the OR gate. Of course, the OR gate here would have two inputs, A, B. So this is the OR gate. If you wanted to implement the OR gate in terms of your universal gates, let's start with the NOR gate first. It's pretty simple because if you invert If you invert the no function, you would get O function. This one is very simply implemented as follows using the no gate. So you'd have a no gate. A, B, so that's your no. What you get here now needs to be inverted, but we just see how to invert using the no gate. If you just couple these two together, and when you apply your no gate again, you would get your OR gate. Okay, so that's your Q here, and that's your Q here. Okay, if you want to add expressions of what are we actually obtaining. Yep, so at this point here, you're actually getting some problem with the annotations. I'll just clear all the drawings and data again. Okay, so I'll just say it if you have your OR gate. So we know this is your A, B, and this is A, O, B. So if you want now to implement that using the NOR gate, so we said we can use NOR gate first. So if you have your A and B this side, so what we're getting here at this point is A, O, B whole complement. That's your, but now you want to, of course, obtain A, O, B. So if you invert that again, and we've seen above how you invert using the NOR gate. Remember, when you're using one universal gate, you want to use only one universal gate. You can't combine the NOR and the NAND together. That's defeating the purpose. So if you now invert that using the NOR gate, both inputs connected together and one input here, so you obtain your A, O, B. Okay. Next, now what you want to see is how can we implement your OR gate again, but using the NAND gate. Okay, this one's a bit more difficult. The steps are actually summarized here. Let's look at them. So we know this expression for the OR function Q is equal to A or B. Now, what if we complement it first? Okay, we complement it. If you complement, of course, the left-hand side, you have to complement the right-hand side. Now you're applying De Morgan's rule. So this is the De Morgan's rule here, which you see. So if you had the whole complement for the OR, it becomes the ending of individual complements. Now, of course, you want to get Q, so you can complement back. Now, what this expression is saying now in terms of the NAND gate, you can see it's a NAND. You are first complementing the individual A's. So instead of A and B here, we want to have complement of A, complement B, which we know how to do using the NAND gate. So you would connect both together. So that's your first, if that's your A here, you would have not A which you want to get. So you just similar thing, you would negate your B as well. Now, once you get the individual complements here, this dot here and complement is nothing but NAND. So if you take the NAND of these two here, you get your OR function. So what you get an output here is this expression here, which is nothing but A or B. So again, you can see we apply the De Morgan's rule in this case here to be able to formulate the OR gate in terms of a NAND gate. If you want to formulate the OR gate in terms of a NOT gate, that's very simple, just invert of it. But the OR gate in terms of a NAND gate, you would have to do a bit of manipulation. Okay, so let's proceed. If you want to implement the, this is what you've just done. Okay. Now, next thing, of course, we try to attempt is writing the AND gate in terms of universal gates. So It's logical again. If you want to implement the AND gate in terms of a NAND gate, that's very simple. You would just have a NAND gate and then invert it using NAND gate again. But if you want to implement the AND gate in terms of a NOR gates, you would have to do some manipulation, and this is shown here. So similar approach to what we did earlier. First, you start complementing, apply De Morgan's rule, and then this is not true. Okay, so this is how we could represent now the AND function in terms of your NOR gates. So you can see here, if you find the formulation we've seen earlier for the OR gate in terms of a NAND gate, and now for the AND gate in terms of a NOR gate, you find some similarity. Like you've seen earlier, discussed earlier, if you want to implement the AND gate using the NAND gate, that's very straightforward. You just invert the output of your NAND gate using the NOT gate, which you've seen earlier. Okay, so as an exercise for you now, you can see how can you represent the XOR and XNOR gates in terms of universal gates. Yep. So if you want to write a mathematical formulation for the XOR gate, this is as shown here. So if you take the two rows here where your output is high, you can find this one and this one. You have two rows here. So in this row, you can see your A is high, so it's not complemented. And the condition for it is you have a NOT, your B is low, so you're ending it. And you have another possibility. So this plus here is O. So you have two possibilities where Q is high, is when it's not A, because A is low, and then B. So how can you represent this expression using the universal gates? Now you already know how do you actually represent the AND, which is N here. You know how to represent the NOT, you know how to represent the O, and N again and NOT again. All this you know how to represent using the NAND and the NOR gate. So this is left as an exercise for you now to represent the XOR and the XNOR in terms of universal gate. Okay, so the next topic I'll be covering in the next video is problem formulation analysis, and also the method that you find that we have used to actually write this expression here will be covered in more details, a chapter on min terms and max term. So for the time being, I'll just ask you to use this expression here for your XOR. And of course, if you invert the XOR, you get the XNOR, which is straightforward. Okay, so do give this a try, and we will cover that in the next short class. Thank you.